Good morning. So we are back to stresses. Today we will learn stresses in 2D and 3D planes. Maybe, maybe if time permits. We learned stresses in 1D plane in the last few classes. So let's go ahead what we learned. This is the syllabus for stresses. Okay. This part we have finished already. We have finished introduction to stresses. We have finished definition of stress. We have finished normal stress and one problem on normal stress, and we have finished shear stress and a problem on shear stress. Today we are going to learn more on stresses in an inclined plane, which we have partially discussed. State of stress, we will discuss this also. We have done it. Equilibrium equations, we will not probably do it today. And stress as a tensor, we will learn it, right? In the next class, we'll probably do stress transformation and some parts of stress equilibrium. Finally, it will end up with 3D stress equilibrium. So this is not different from the other two, so it will not take much time. Okay, little bit of recap. We have discussed that stentometrial is for three kind of S, so it's called 3S of stentometrial, 3S: strength, stability, and stiffness. Right? We have discussed at large what are these things, and they depend on strength depends on material property only, as long as it's elastic strain. Okay. And then there is stiffness and stability, which depend on the geometry of the structure as well as boundary conditions. We discussed about how to get stresses. So we said that stresses depends on internal force. They don't depend on external force. Stresses depend on internal force. Never forget this, internal force. No matter how is your external load is distributed, or how is your external load is given, the stress will definitely always depend on internal force. If the internal force change, stress will change. If change in loading pattern doesn't change the internal force, then your stress will not change. Okay, so this is an important point to note. And the definition of stress is limit area A changing to 0 delta F by delta A. Okay, and delta is around the point F, where the point F is around point where delta F is working. We also discussed about average normal stress, where we have said that Saint-Venant's principle apply. We showed with an example with a classroom demonstration, Saint-Venant principle, and we all saw, right, that this guy will be, the stresses will be higher near where the load is acting and non-uniform, but stresses will gradually become uniform as you go away from the location of application of load. This is only not for the location of application of load. It also on various other things. For example, sharp change in geometry. Okay. Two is application of load, location of application of load. And three is support. At this location, stress will not be average. Be uniform. Okay. So that you have to remember, and please note when you design. So many of you join C5, right? So you design a lot of parts for various kind of competitions that you go for, right? So for one of them is our racing car. So please note, while designing those parts, you have to take care of this kind of idea that average stress is not uniform, or there is no uniform stress near the application of the load or the location where there is a sharp change in geometry. For example, sharp change in geometry meaning something like this. You have a bar like this, suddenly you are changing the bar cross section. Okay, so that's a sharp change in loading, a sharp change in boundary or geometry. All right, so this kind of materials if you make, then they are easy they are prone to breakage easily at this location, okay, or this location. So make sure that you design them properly. Now let's look at normal stress and shear stress. We defined normal stress and shear stress in the last two classes, and this is what we have described with we have taken a bar member, right? A bar is an axial member which carries axial load. So there is axial load that are given to the member. Now, if you take a cross section here around point P, then you get again the same force because it has to balance both sides is P and P. The cross sectional area at this location is A, and therefore the stress you will assume to be uniform because it is far away from the point of location, point of application of force. So this is going to be uniform, and then your normal stress is given by sigma equal to P by A0 if your area is A0, okay? Area is A0. All right. Similarly, for case of a shear stress, which most example for pins or for nut and bolts, pins, bolts and nuts, right, where shear stress are more prevalent, the shear stress acts along the grazing surface, and therefore, as you can see, if you take a section at Q, that's the grazing surface, and it acts with P. If the area of cross section is A, C cross section, okay, this area is A cross section, then your shear stress is P by A cross section, right? So this is going to be P. Okay, and we have seen some examples doing this. Now let's look at what happens when you incline the plane on a bar member. Okay, we are looking at a bar member. We were looking at normal force. So when there was no inclination in the bar member, the load that we had, the stress that we had was only the normal stress sigma, right? Because the cross section is normal to the load application, and we are looking at this only. So it was sigma x, right? So sigma xx is P by A0. But one of you can say me that, sir, why should I have to always take a vertical cross section? I can take a cross section at any angle with the vertical. I say yes, you can take cross section at any angle with the vertical. So let's say we made an angle theta with the vertical, and if you make an angle theta with the vertical, and you take a cross section here, right? So this is the plane of cross section. I hope all of you can see. I can enlarge it. Yes, this is the plane of cross section. Okay, that's making an angle theta with the vertical. If it makes an angle theta with the vertical, then my load is like this. Okay, this is my load P, as you can see. It goes horizontally like this. So that will also make an angle. I can. Okay, let's take the cross section. So I've taken the cross section, so it has been cut out now. The other part is gone. So this part will have P force. It has P force, and this P force, now I can draw this P force. One is along the grazing surface, right, and one along the normal of the plane cross section cut, right, because I need stresses to be along the grazing surface and stresses to be normal to the surface. So I have to take components of this P force along the normal and along the grazing surface, right? And if I do that, I'll get two kinds of P. What will be this angle here? This angle is going to be theta. I have shown that here how it can be theta. So that's a theta. So if that is a theta angle, then this is going to be my P cos theta, right? And this is going to be my P sin theta. Now look at the area here. My earlier area was vertical like this, right? Now the area is inclined. This is my area. So this P force is now acting over the bigger area, right? Okay. This is the bigger area because this is inclined, and this is the smaller area because this is vertical. That gives you the smaller area. So if your vertical area is A0 and your inclined area is A theta, the relationship between these two areas is A0 by cos theta. Okay. All right. The area is going to increase, right? Because the minimal area is the vertical cutout, so it's going to increase. So, and therefore you have to divide it with cos theta. So area is A by cos theta. That comes from the normal also. Now what we have to do is, we know the normal force, which is P cos theta, and we know the shear force that is going along the grazing along the surface is P sin theta, right? So these are my two forces, P cos theta and P sin theta. Therefore, normal stress will be normal force divided by area. So P cos theta divided by A0 by cos theta, and it gives you P by A0 cos square theta. Now you can see my average stress when I was having a vertical cutout was P by A0, right? Now it has changed with P by A0 cos square theta. All right. Similarly, my shear stress, which was 0, right? In this case, there was no shear stress, remember, because there was no component of the force that was grazing along the surface. So shear stress was 0. Now there is a shear stress that is appearing because there is a shear force that has come into play. So that will be V by A theta, and that comes out to be P by A0 sin theta into cos theta. Okay. Up to this, I hope this is clear. Now, we are looking at a 1D, right? We are not looking at 2D. We are looking at 1D here. And therefore, we are getting this too. So normal to the areas, this is okay. Now, if I ask you how do you say this is changing? No, this force is changing. Now, before I go there, I want to ask you one question. Why do you think I need to take a plane that is inclined to the vertical plane? Is it just for fun that, yeah, I want to take a plane that is inclined, I'll take it? Or is there a reason for doing it?
Sir, what if the beam is bending and we have to take shear for bending? So for bending, we should take the tangent for the curve and then we try to find the shear, right?
Archis, we are not talking about beams here. We are talking about only axial members here. Okay,
okay,
beams
still,
will just
like if the axial member is bending, then I mean, in that case, we have to consider shear stress along a plane, inclined plane.
okay, Archis. Can we discuss this offline? After the class is over. Okay, I have to discuss a lot, so all of you should be there. Nobody should leave. Yeah. Anybody else has anything else to say?
Sir, what if the breaking stress is very low for the material, sir?
Okay. What if you want? You mean what if the breaking stress is very low?
Sir, like you were saying, how is this useful, sir?
Okay. Okay.
So, like, if you, instead of keeping a normal cuboidal beam, if you just cut it at a plane, the stress applied will decrease, na, sir? The
Okay.
stress of surface.
Akhil, it might decrease, it might increase. We'll talk about this.
Okay.
Some cases it will decrease, some cases it will increase based on what angle you're taking the inclination.
Yes, sir.
So it will be more clear in the next class when we do stress transformations. It will be more clear at that point at what angles it will increase and what angles it will decrease. Okay. But yeah, it can have both effects, increase and decrease. So as you can see, it is P by A0 cos square theta here and P by A0 sin theta cos theta. Okay, I'll tell you why we need to take inclination. Now, this member is an axial member, okay? So when I say this member is an axial member, no matter what, this member will only have axial force. It will not have bending force, okay? It will not have a transverse force acting on it. A transverse force gives rise to bending. This is not a transverse member. This is not a member that carry transverse load. This is an axial load. So therefore, this member may be a truss member, okay? It never carries a bending load. It only carries axial load. But even then, the member may be made up of wood, okay? So let's say I have made this material out of wood, okay? And let's say the fiber of the wood are along this direction. Wood have fiber, right? Wood material has lot of fibers in it, and they are seen from outside, right? So let's say the fibers are like this. Now I give the material a load, axial load, because this is an axial member. So I have given an axial load P. And I'm very happy because its normal stress sigma along zero axis, theta equal to 0, is lesser than my sigma allowed. We have done this problem last class, right? I'm very happy that sigma at theta equal to 0 is lesser than sigma allowed. My design is over, pakka. I am very happy. Your client is very happy. Everybody is very happy. But suddenly, you see that there is a crack that is developing in the material along this direction. Okay, suddenly you saw it. And then you want to see what went wrong, right? You want to go back and see what went wrong. You know, why it's suddenly breaking from that direction? You know, it's very crazy. My design is perfectly safe. What wrong did I do? The point is, when you looked at this stress, right, you looked at a plane that was this. Okay, you did not look at this plane. What will happen at this plane? What are the stresses acting at this plane? Where were these stresses higher than this and higher than this? Or the stresses were lower than this and lower than this? You did not check that. You need to check that. First point. Second point, you check for normal stresses. You did not check for shear stress. Did you check that it is less than tau allowable? You saw there is no shear stress and you said tau allowable is not necessary. But as you can see from this diagram that we have here, that there can be shear stresses that are acting in an inclined plane. And therefore, those shear stresses can go beyond my allowable shear stress. And it can start a failure. And if there is a shear stress along this plane, you know that this plane is going to move this direction and that plane is going to move that direction, right? Because the fibers are aligned in this way, so they can easily break away from each other, right? And they can move on in direction, so it can fail in shear, which you did not check. Therefore, as an engineer, your objective will be to check every direction of the cutout plane, at which plane it can have maximum stress, and along that stress, along that plane, you have to check sigma allowable, okay, and tau allowable. So you have to find out which plane gives you maximum stress, right? Maximum shear stress, and which plane gives you maximum normal stress. These planes are called principal planes. We'll talk about this maybe next class, but they are called principal planes, and we need to find out the direction of these principal stresses and whether the principal stresses are lower than the given allowable stresses in compression and in tension. Similarly, the shear stress that you get, maximum shear stress, is it lower than the maximum allowable shear stress or not? So you have to check that. So that's why this example comes into action, that this tells you that there are orientations along which the stresses can be higher, okay, which is generally not seen in the regular orientation of the member. So a regular orientation of the member will give you sigma normal, but no shear stress. But you can see here the formulas, right? I can go to the next slide and I can see the formulas. You see the formula here. Your shear stress is P by A0 sine theta cos theta, right? So at theta equal to 0, what is its value? It's 0, right? At theta equal to 0, see this graph, it is 0. At theta equal to 0, it is 0. Now it grows up, grows up, grows up, grows up. Maybe at 45 degree it is maximum. And then again go down, go down, go down, go down. Theta equal to pi by 2, it will be again 0, right? So this is 0, pi by 4, pi by 2 probability, right? So at 45 degree angle, there is high shear stress, that is maximum shear stress, that is acting onto the plane. And that will be 1 by root 2, 1 by root 2, I think, right? Or half and half, I forgot. 1 by root 2, 1 by root 2, that will be half. Then it will be P by half, P by 2A, 0. All right, that is the maximum shear stress that is acting onto the plane. But for my normal section, normal geometry and normal cross section that I take, there is no shear stress. But finally, it comes out at 45 degree, I have a maximum shear stress. Similarly, you look at the normal stress. The normal stress is P by A0 cos square theta. So it's maximum at this point, right, is equal to P by A0, and then it will slowly die down and come here at pi by 2, it will be 0, right? Right, this, it will not be completely like a cos because it is a cos square, so the slope will be little down, so it will be like this. All right, so maximum of the shear stress is at theta equal to 0, and its minimum in the sense 0, magnitude wise minimum I'm talking about, is at pi by 2, which is 0. Okay, so these stresses keep changing based on the plane. So if I have an inclined plane that I have told here already, the material can break at that inclined plane because of shear stress acting there, because the shear stress is maximum at that point. Okay, same thing has been discussed here. Let's say case 1 is I have a vertical cross section. Case 2, I have an inclined cross section that is 45 degree, and then case 3 is negative 45 degree. Okay, 3 cases are drawn here. Fourth case, for theta equal to 90 degree, is left for you to do. Okay, I have already told what will happen at 90 degree. Please check yourself what happens at 90 degree, whether that's a true or not, but means it is 0 here and it is 0 here. Okay, please check yourself. Now, normal sigma is given by P by A0 cos square theta, tau is given by P by A0 sin theta cos theta, right? So what is the maximum value? You can find out. So maximum normal stress is at theta equal to 0. I have already told, I've drawn the diagram. And maximum shear stress at plane theta equal to 0, shear stress is 0. Tau is 0 as maximum sigma location. Please note this. This is very important. Tau is 0 at maximum sigma location. And this is not stray case like this, but it is true for all, everywhere, wherever we do some analysis, shear stress will be 0 wherever sigma is maximum. So this is universally true, so keep this remembered. Okay, maximum shear stress occurs at plus minus 45 degree. So maximum shear stress occurs at plus minus 45 degree, that we have checked already. So here there will be maximum shear stress, and similarly it will go back like this or maybe like this, and you'll get maximum shear stress again here. Okay, so it will be multiple, so 45, then 135, something like that. So, and that should be equal to sigma dash. Sigma dash at 45 degree is also same. Okay, at 45 degree cos square theta is also on half. So this is P by 2 is 0. Please do this slide, do it yourself. This slide is do it yourself again. Do it yourself again, okay? So that you get a hold on this. Okay, we looked into, this is a part of stress transformation. We will learn more stress transformation for 2D materials in later part of the course. But we understood that transformation of stresses are important, okay, because in some direction the stresses may have maximum values, and that may create the member to fail. Okay, so we need to check all the directions or all the planes, theta, for all values of theta around the vertical plane. Okay, now state of stress at a point. What do we mean by state of stress at a point? We discussed it in the last class, so I'll go quickly. State of stress at a point is number of unknowns, okay, at a point, number of unknown stresses at a point, okay, number of stresses at a point. I'll not write number, I will say unknown stresses at a point. Okay, it may not be number only, it can be number and then names also, right? So unknown stresses at a point in a continuum body. When I say continuum body, it's a continuous body. Okay, a beam, a structural member, anything can be continuum body. All right, so this we have seen in the last class, that you assume a point within a bar member. This is a bar member. You assume a point within it, and then what happens? You take a very small cube around it, right? So this is what has been shown. You take a section, and this is the cube, right? And we saw that for this I can draw only this one, right? Sigma xx, right? But when you incline that plane, as we have seen in last example, when you incline the plane, you get both sigma and tau. So I don't know which plane is this, so I'll write it as sigma n and tau ij. Okay, nj I can write because n is already given. All right. So both shear stress and normal stress start acting if you change the orientation of the plane. All right. So this is how it has been done. You take one cross section here, and then you take another cross section here. Then you take one cross section horizontal, another cross section horizontal. All are dx and dy apart. So you get this point Q, and that's how you do it. And the load is going to be P by A here. And since it has to balance, so this is sigma x, it also has to be sigma x because both side area is dx dy, right? Or dz dy. Okay, so both side it has to be same sigma x. So this is balance of forces, equilibrium. Okay, from equilibrium equations. Into, or I'll write P dash into dy dz equal to sigma x into dy dz. Therefore, sigma x. So this is dash equal to P by A. Okay, so both sides will be equal. All right. So that gives me that both sides will have same stress acting. So this diagram is very important. Now let's go to next one. But for an inclined plane, the inclination will give rise to shear stresses. So I'm just drawing the figure a little bit up. It will give rise to tau m, that means shear stress here. And as we have discussed in the last class, that shear stresses, complementary shear stresses will be opposite to make sure that the rotation is stopped. So therefore, we can see that this is acting this direction, this will be acting in the other direction. If this is acting this direction, this will be acting on this direction because of vertical force balance. And then this will be acting in this direction, that will be acting in this direction to make sure that the moment is balanced, right? Okay. So in 45-degree angle, your sigma value will be tau max, will also be again P by 2A. Just for the same example that we have drawn, right? So in a nutshell, you cannot draw 3D. It's not easy to draw 3D all the time. So what we do is we draw a 2D diagram like this. This is a 2D diagram for the bar. So there is a P force acting here. There is a P force acting here. There is a P force acting here. This is my XY direction. This is how you draw. So you point and point A and along its surface. So if this element, you can see this element is oriented normal directions, right? Normal XY direction. So this is going to be sigma. This is going to be sigma. There is no stress acting, shear stress acting, right? I have not drawn any shear stress, so it's not acting on it. Now, if I make that angle a little bit inclined, let's say this theta angle. So this plane is also has inclined. You see, my diagram of the plane is also inclined. So this is how you represent engineering representation that the plane has taken now inclined plane. So inclined plane will have both shear stress and normal stress, right? So this will be shear, this is normal. So if there is a shear stress along this direction, this shear stress is going to be opposite to that direction, right? And this will create a moment which will be like this. So there has to be shear stress that should balance this. So this shear stress will be this direction, that shear stress will be this direction. Okay. As you have a normal stress along this direction, that plane will also have a normal along that direction. Okay. Clear? So this is how you draw the represent the stresses. So remember that these two are perpendicular to each other. So one plane that was taken maybe 45, the other plane that was taken is minus 45. Okay, like here. We have shown this here, right? Yeah. One plane was taken like this, the other plane was taken like this, right? So if you join them, the plane is going to look like this. So if you join them, one plane is this one, the other plane is this one, right? And then you make it a square or a cube or a rectangular section. All right, this is 45-degree angle. So this is obviously becomes now minus 45-degree, right? This is minus 40. So that's how we represent. So we represent at a time two planes perpendicular to each other. The reason for that we will tell you in the next class when we do more circles. We will tell you why two planes are necessary. All right, clear? So that's how you represent. So two planes perpendicular to each other. Here also, if you see, there are two planes. One is this one where normal stress is acting, and in this plane there won't be any normal stress acting because this is 90-degree, right? At 90-degree, we saw that the normal stress and shear stress both 0 at 90-degree, right? Here, so both 0 at pi by 2. So that plane, on that 90-degree plane, they both have to be 0. So this is 0. So there is no normal stress acting here, neither shear stress acting there. Okay, but here there is only normal stress acting. So we represent stresses at two mutually perpendicular planes stresses get together. All right. Okay, this is only shear stress. So this is for only shear stress, no normal stress. So when there is only a shear stress, then you take this section, okay, and then that section will have one shear stress acting here on the surface, and that is along this direction. If you see along this direction, so the bottom portion will have that direction. So the bottom portion has got that direction, and therefore these two will be arranged based on the rotations, right? So it has to go in this way, and that has to go this way. So complementary shear stresses will be equal and opposite direction. So rotation will be opposite, right? So you can represent this plane, this in a plane like this. Okay, this is my Q point, and the stresses are going to be like this, like this, like this, like this, right? Okay, and they will be same. So tau, 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 tau. All right, that's how you represent. So tau is not going to be E by area of cos. Okay, so that's how you represent stresses, normal stresses and shear stresses in a plane. Now, general state of a stress. Now, so we have discussed this also. So if you take a point, assume a cube around that point. So there is an area A, and we have discussed that there will be a force, one force normal to the plane, the one force will be grazing to the surface, like as shown here. Now the grazing to the surface can have two direction, one along y and one along x or z, one along y, along z, and therefore you can represent that force as one along x, one along y, one along z, and the stresses will be sigma x, tau xy, and tau xj. This is what we discussed in last class, right? So I have three stresses here. One is sigma x, tau xy, and tau xz, right? These are the three stresses here. But that's not all. Wait, don't run away. Now this point, the same point, okay, can be represented from the left half as well as from the right half and the left half. This is my left half, that right half, this is my left half. Okay, and in the left half also you will have similar stresses, sigma x, tau xz, and tau yx, right? So doesn't matter which side you're looking at, they will have same stresses as long as there is no extra force acting at that point itself. So this side is going to be same, that side is going to be same. Now let us take a cube around that point, small cube. So this is small cube that take around that point, right? And let us represent only by a cross section of that cube. So this is my cross section cube. So we are looking at a coplanar case. Okay, we are not looking at 3D. We are looking at a coplanar case. So we are only looking at a plane around Q point. Now, if I take that plane in XY axis, so that plane is taken along XY axis. So Z axis is not material to me. So it's not an inclined plane. It's a plane along XY axis. So along this surface, you can see that there is a sigma xx that is working. And along this surface, there will be tau xy. You remember that, right? Tau xy. Tau xy in the sense x is the direction of the plane, which is perpendicular to x-axis, and y is the direction of the load, so along the y-axis. Okay. Similarly, if you look at this plane, so we have to, as I said, we have to represent in two mutually perpendicular planes. So if you look at this plane, so that plane will have sigma yy, right? Because y is the direction of the plane and y is the direction of the load. And then this will have along this direction, so tau yx. Okay. Same. So if this is sigma xx, so this side is going to be sigma xx, and there will be tau xy along this surface, and therefore tau yx also along this surface. Right. So what is the state of stress at this point? So I have to know the state of stress at that point. The state of stress at this point is given by all these forces. Okay, all the forces that I represent here. What are the forces that I have? Sigma x I have, sigma yy I have, right? This is also sigma xx, sigma, this is sigma xx, this is sigma y. So they're represented again. So I can write only one of them. Now tau xy I have, right? This is also going to be tau xy, they're going to be equal. So one of them is okay. This is tau yx, and this is tau yx. So that will also come here. Tau yx. Okay. So the state of stress at that point is going to be this 4.
Yeah.
Okay. Now, from a complementary stress analysis,
Yeah. So see,
we know that. Okay. Can you hear me now, all of you?
Yes, sir.
Okay. So the state of stress here, we have 4 right now. This 4 can be reduced further, right? Because tau xy is equal to tau yx. We know that complementary states are equal. So my stress, in that is going to be, there are 3 stresses that are going to be, and I can write them in a matrix format. Sigma x, right? Sigma yy, and there will be here, let me rub it a little bit. Yeah, sigma yy, this will be tau xy, and this will be tau x. These are my 4 stresses, but these 2 are equal. Therefore, it's a symmetric matrix. All right. So there are 3 unknown stresses. Notation of stress I have already talked about. This is how you represent stresses. So first x represents the direction of the section at which the cutout is taken, and the other x is represents the direction of the force. So since it needs 2 directions, it is called a tensor of second order. Okay, a stress is a tensor of second order. A vector is a first order. Now, why second order? Because you need 2 indices. One is x, the other one is y, or I and j, right? So this is also written shown here with this picture here. So you can go through this and understand it better. All right. Okay. In matrix format, as I said, we can write this in matrix format at sigma xx, tau xy, and tau yx, and tau yy. A stress is a second order tensor, right? So it is represented not by a vector but by a matrix, right? So I'll write that also here, and is represented using matrices. Okay, so they will follow matrix addition rule or matrix multiplication rule. All those things will be followed by a stress of second order. So whatever matrix rules you have, they all will come and act on stresses. For example, whatever row mathematics or row operations you can do, they all can be done on vectors, right? But they won't be able to be done on stresses, because stresses are matrices or tensors. All right, so this is what I've written. You can represent a stress tensor at a point as this. You see that, please note that the third plane has all 0 because we are not considering the third plane. We'll talk about that plane in the next class. I will stop now.